Okay, so let's start the class. Remember tonight, at 6 p.m., you have test number 3, but you don't have to take it at 6, of course, right? It's a 5 hours. It's a window for 5 hours. So if you want, you can take it at 8 or 9. So it should be an hour and a half, but be prepared, okay? Check your connection, internet connection. Make sure you take it on a laptop. Make sure you have a tablet. Don't take it on your phone, okay? And then because if you miss the test, the makeup will be in my office in 8 a.m. and it won't be the same. It won't be the same. So make sure you don't miss it. It's more like a assignment online. So the topics are torques, equilibrium, and then conservation of energy. No. What did I say? Torques, equilibrium, and conservation of momentum. Okay. Okay. So I want to go back. So there is one thing we didn't do together, and it's about Hooke's law. So I'm just opening a small parenthesis. It's not on test 3, so I don't have to worry about it. But just a small parenthesis here. If you have a spring here and you're gonna have a mass attached to it, you see the spring is gonna stretch out, and there will be what we call a restoring force. There will be a force that wants to bring back the spring to its initial length. So you experience that if you do Pilates, for example, you can stretch it and you feel the restoring force, right? So let me ask you something. As you're gonna stretch more, is the force the same, or is the restoring force get larger and larger? Very good. And it's gonna be proportional to the stretch. That's the idea of exercising, right? So it means more stretch, larger is the stretch, larger is the restoring force. So Hooke's law, it's a very simple equation. Hooke's law says the following, that if you have a spring here, so this is the length, the rest, at rest, okay, it's not being stretched. So now you're stretching your spring because there is a weight pulling down. There will be a restoring force here, right? I want to bring back the spring to its initial position. That restoring force equals to a constant, which is the spring constant. So just a constant that depends on the spring. You know, if it's a very flexible spring or if it's a stiff spring. So stiffer the spring, larger is that constant times the stretch. So for example, in that case, you see the spring is being stretched by an amount of x, okay? So the restoring force will be equals to kx. The minus, it says that it's a restoring force. So when you think about gravity, for example, you have a mass here. You move that mass above the ground or above the table. You can think of gravity as a restoring force. Okay, it's like an invisible spring that wants to bring that notebook back to Earth. So in that case, the restoring force will be mg. Okay, and the potential energy is mgh. But it's like you have a restoring force. And each time you have a restoring force, you can have potential energy. So anyway, so this is easy to understand. You can even do some, you go to a gym. So this is not being stretched, nothing happens. If you put 5 pounds, okay, you can see by how much is being stretched. If you have 10 pounds, it's going to stretch twice as much. If you have 15 pounds, 3 times as much. So it's a proportion between the restoring force and the stretch. Also, when you are doing work on that, you are storing energy in elastic potential energy. And when you let go, it's going to turn into kinetic energy, right? So anyway, I wanted to show you that. So in that case here, I have 50 grams and the stretch is about what? What do you read here? About 10 exactly. About 10 or 19 centimeters, right? 9 centimeters. About, you start from here, go down about 9 centimeters, right? So now if you have twice as much, so instead of having 50 grams, you have 100 grams, what do you expect? Almost 20, exactly. Exactly. So that will be 18, exactly right. Right? So you don't want that to oscillate. It's going to be about 19 or about 20. So twice as much. So twice the stretch, twice the force. Now here, of course, it's in equilibrium. So let's review for the final, for example, it's in equilibrium. So what are the forces acting on it? mg, excellent. You have mg. Okay, you have to convert grams to kilograms. And now you have the force here pulling it up, which is equals to kx. Okay, the restoring force. Up equals down. So you have kx equals mg. And for example, you can find the spring constant. So this is just a constant. It depends how stiff is the spring. So if you have a very stiff spring, the spring constant is going to be very large. Depends also on the initial length of your spring. It depends on the cross area, but it's like it depends on the spring. It's like a blueprint for your spring. Is that clear? So if you have 50 grams, it's going to be 9 centimeters. If you have 100 grams, it's going to be 18 centimeters. And what about if you have 250 grams? About 50 centimeters. So if you go from 9, 27. 45, excellent, excellent. You see, it's a proportion. It's a proportion. So what's the proportions? For each step of 50 here, you increase by 9. So this is called the slope. So it's a linear relationship between the restoring force and the stretch. Does it make sense? So let's verify. If I put 250 here, it's gonna be about 45. Supposed to be about 45. Let's cheat a little bit. 45. Agree? So you can do that, like trying to find ideas for you. If you want to do a demo, you don't have to, but here. So of course, if you don't have a spring, you can replace it by a rubber. Like if you go to the gym, they have those rubber bands, like elastic.
I have one here. It's not a very expensive.
So you have a spring here, and here you have the load, and the restoring force equals to the weight of the load. Thank you.
Spring, you see it here, and there is here a holder onto it, so it's already a little bit under stress. That doesn't make any difference. These marks here are 13 centimeters apart, and every time that I put 1 kilogram on, you will see that it goes down by roughly 13 centimeters. It goes down to this mark. I put another kilogram on, goes down to this mark. I put another kilogram on, and it goes back to this mark, all the way down. And if I
So you see, you multiply the load by 2, the stretch is multiplied by 2. Okay, so it's a linear relationship between the stretch and the load equals to the restoring force. So this is called Hooke's law. It's named after Robert Hooke. He was a contemporary of Newton, and they hated each other. Maybe I told you about, maybe you know Robert Hooke if you are in biology, because I think he's one of the first one using a microscope who discovered the cell. It was not a living, I mean, it was not a cell from an animal, it was a cell from a plant, like the onion. You remember in high school, the first thing that you look, you slice an onion and then you look at cells, at that cell through a microscope. That's Robert Hooke. And Newton didn't like him at all. And I told you the story, right? He made fun of him because he was deformed. Hooke, he had a small size. So Newton said very famously, if I have seen so far, it's because I'm standing on the shoulders of giants. So I am a giant and you are a dwarf. That's what it means, right? It was not that nice. But that's for the story. And Hooke died before Newton. So Newton took all the portraits of Hooke that was in the Royal Institution of London. He really had a beef against him. Which is interesting because, you know, history repeats itself. It's no different today. Okay, so the other thing I want to bring your attention to is that when the spring is stretched, then you're going to store elastic potential energy. Okay, so we talked about a lot gravitational potential energy. So you have an invisible spring that is trying to bring back to a lower level of energy. Same thing here. Okay, you're gonna store because it has done work on it. So you are storing elastic potential energy that you can release if I don't know, oops, you see, release everything in kinetic energy. And what's the equation for that? We just touch on it, but it's a very simple equation. Okay, so that's the amount by which the spring is stretched. Okay, so X. So the elastic potential energy is 1/2 K, so that will be the spring constant. So if you have a very stiff spring, you're going to store more energy because it takes more work to stretch it out. So you can do more damage. Okay, you can hurt someone more. And then X, and then here you have a square. Okay, so in your book, Johnson and Cotnell, he talks about Hooke's law and elastic potential energy. So you are supposed to use your textbook. Now you can swing if there is no friction. So let's remove friction, okay? And I'm gonna pull it here, and you see how it's gonna oscillate. So do you see here? No kinetic energy increases, then it's 0, increases again, then it's back to 0. So kinetic energy maximum, 0, maximum, 0, maximum. When kinetic energy is 0, you have elastic potential energy. And I guess you also have gravitational potential energy. So you see, it's swinging back and forth between elastic potential energy, gravitational potential energy, and kinetic energy. If there is no friction, the total amount of energy, which is called mechanical energy, will stay the same. So, example, I always give that example, especially this is the right time to take that example. If you have Bitcoin, okay, so you can have a given amount of Bitcoin and then you cash in. So now you have dollars and Bitcoin, but the total amount will be the same, especially because there is no commission. Okay, you can swing back and forth between dollars and Bitcoin. The total amount will stay the same. Good for you if you have Bitcoin now. So that's for the story. And you see how it's oscillating up and down. So if I look here, so you see, this is called a simple harmonic motion. There is no friction. So the energy will swing back and forth between kinetic and potential and elastic. And you see that here, what you have is the displacement. So it means it's the stretch by how much the spring is being stretched. And so here you have no stretch, maximum stretch here, or compress, it's being compressed, zero stretch, maximum stretch, no stretch. What is that function?
Sine.
A sine, very good. So you're going to have a simple harmonic motion each time the displacement as a function of time describe a sine. And this is happening each time when something is oscillating. It will be acted upon by your restoring force, which is proportional to the displacement. So each time that happens, you have what is called a simple harmonic motion. The velocity, so you see maximum velocity, zero, zero velocity, maximum velocity, zero velocity, maximum velocity, zero velocity, and so forth and so on. The velocity also follows a sign. The acceleration is maximum here. It's going to be zero here, maximum, because the acceleration is proportional to the force. So when the restoring force is maximum, that's when you're going to have a maximum acceleration. Okay? So it's just for those who want to take the MCAT, for example, they might have questions about Hooke's law or elastic potential energy, but it's not that hard to understand. Okay, so I had like uh, I don't know, I have a very nice GIF, but I don't know if I can find it. I don't know if I don't find it. So
Is it the one on the top?
this one, I had like a GIF. So here, it doesn't matter if you compress your spring or if you stretch it out. The equation for the restoring force is always K times the amount by which the length was changed relative to the initial length. Okay, so this is Hooke's law. And I had a great, I don't know if I want to find it because it's going to take me time. Flipping physics. So it's a great website. And he has also a YouTube channel. I'm not going to find it because when I want to find something, that's when I'm gonna find it. Oh yeah, we just have to be patient. Okay, so you see it's being stretched. Okay, so that will be your stretch. So the restoring force will be K, the spring constant times the stretch. And now it's being compressed. same thing. You're going to have a restoring force that will be equals to kx, and k is a constant. Is that clear? So that way you visualize it. You can come up with so many demo. You can have a spring, and it will be harder to do that. It's easier if you have a Pilates band. Okay, so you compare one is at rest, you put 5 pounds on, you see the stretch, you put 10 pounds on, you see the stretch, 15 pounds on, you see the stretch. And you can do that at the gym, so you don't have to buy anything. Okay, so that was the parenthesis here. Okay, so let's go back to conservation of energy. Okay, so let's do this one. So again, conservation of energy, the total amount of energy before equals energy after. So potential plus kinetic before equals potential plus kinetic after. So very simple. You see, we should start with, I mean, kinematics is not easy. That's what it is, okay? But I want to follow the textbook. That's why, otherwise it can be confusing. And of course, you want to open your textbook, especially if you are taking the MCAT, you want to go to physical therapy school or whatever, medicine or medical field. So, you strengthen your skills as we go along. It will be easier because otherwise you're going to forget everything. And take notes. Okay, so what's happening? You toss. So this is your hand. And there was the speed here. That's the initial speed. So don't forget everything, of course. You can decide that potential energy equals 0 here. So that's still your hand. Now the tennis ball is going to go above your hand and it's going to stop here, right? So the velocity equals 0. And then we already did something like this last time. So that's why don't forget everything. Don't rely on me, okay? You have to work on your own. You have to do your homework, blah, blah, blah. So that's before. That's after. So what does conservation of energy says for now? You have the total amount of potential energy, so it could be elastic, in that case gravitational, plus kinetic energy, that will be before, equals potential energy after, I'm going to put a prime, plus kinetic energy after. So does it have potential energy before? No? So 0 plus kinetic energy. Yes, so 0.5 the mass, 20 square. So you see, it works like momentum, except now we have energy, which is easier because kinetic energy is a scalar. Remember, for test number 3, momentum can be negative. If it's moving to the left and you decide left is negative, momentum will be negative. So be very careful with that. If something is moving to the left, momentum is negative. So before doing conservation of momentum, the first thing you want to do is which one is plus, which one is minus. It doesn't matter as long as you stick to your protocol. For conservation of energy, don't worry about it. It's not vectors, it's scalar. So it's even easier. So here we have mgh. You see that the mass does not matter, which we are not surprised because it's a free fall situation. Only gravity is acting. I don't know what we want. The height. Thank you. So h will be 0.5, 20 square, and then you divide by 10. So that will be 400, 200, 200 divided by 10. 20. So 400 divided by 2 is 200, divided by 10 is 20. Is that clear? So let's review for the final. So by the way, the final, the date and the time is pushed on Earth. So plan ahead. No makeup because I'm gone. Okay, the week after the final, you won't find me. I'm disappear. So make sure not to miss the final. So if you have a conflict, I will wait for you the same day that you come from MMC. Hopefully it's not a big conflict, but don't miss the final. So anyway, remember kinematics? We used to have this equation that we used a lot, the final speed square equals initial speed square plus 2 times acceleration in that case is g, so minus 10, okay, times the displacement, so the height. So final speed here is 0 equals initial speed square 20 square plus 20 times minus 10 h, and you're going to find the same thing. Okay, so conclusion in kinematics, we just use this equation without really understanding it, but it comes from conservation of energy. So you can solve using conservation of energy, or you can solve using kinematics. Agree? It's easy, right? Like if you do it now with me, it's like reviewing for the final. Time is gonna go really fast. So it means, what does it mean? It means, remember Galileo, the mass does not matter if you are in free fall. That means if there is only gravity acting on the mass. Doesn't matter. If it's a brick or tennis ball or whatever, it doesn't matter. Okay, so let's try to do this one. So if you use Newton's second law and or kinematics, it's gonna be a headache because it's a projectile motion, and you have to find the x component of the velocity, and you have to find the y component of velocity, and then you have to find the speed using Pythagorean theorem. Headache. Instead, we're going to take a shortcut and we're going to use conservation of energy. So before, what kinds of energy does it have? It has kinetic, very good, and potential, very good. At the end, it has kinetic and potential. And the question is, find the final speed. And it's all scalars. We don't worry about x component. Of course, it's going to have an x component and a y component. We don't care. We only care about initial, final. That's it. So that slide comes from your book, Johnson and Kuttner. Just saying that you need to open your textbook. Very important. You cannot rely only on me. Can't. Not possible. So don't stare. Staring is not healthy. Do it. So it's not hard now because it's just scalars. You don't have to worry about plus, minus. So more you do now, that will be on the final, okay? Things like this. More you do now, less you have to worry about the final because you're going to have all your other finals as well. So if you do it now, it will be easier. Don't wait. Don't say, oh, I'm going to wait to be home and I will review. No, don't do that. So gravitational before plus kinetic before equals gravitational after. I'm going to put a prime plus kinetic energy after. So that here, okay, that's where I'm going to say that the potential energy equals to 0. Okay, it doesn't matter where you choose your reference level. Don't stare. Do it. Do it. Potential energy is mgh. Cannot be easier than that. Kinetic energy is 1/2 mv squared. So do it, don't stare. So gravitational potential energy here, you have the mass, then G, and the height 70, plus 0.5, the mass, 38 square, equals, after you still have some potential energy left, plus 0.5 m, and that's V final square. And physics stops, algebra takes over. And even for biology, you need algebra. When you're going to do advanced biology with some statistics and survey and things like that, you need algebra. Yeah, it goes bye-bye, 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 bye-bye. And you are solving for this. So you can do it. Huh? You're doing it? Do it, 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 do it. Okay, with your TI, 7 times 10, 70 times 10. Okay, plus this, so plus 0.5, 38 square. Is that right? Okay. You move this one on the other side to isolate your expression here. You move it to the other side. So minus 350. So now this is isolated. So you divide by 0.5 on both sides. Okay, that's good. And whatever is left, maybe I did a mistake. Did I do a mistake? Did I do a mistake? It's possible. Huh? Then you take the square root. Do you get that? Right? You have to know how to do it, right? It's just algebra. Very simple algebra. That you cannot. You have to know how to do it. Or otherwise you have to retake algebra. Agree? Okay? So physics stops here, and this is just algebra. So make sure you all do it. If you have any question, let me know. So you see they do it as well. It comes from your book. Okay, so they do it even better because they keep the algebraic expression till the end. So it's a good practice to do that. Okay, let's try to do this one. So you go from elastic, kinematic, potential. And here you do have potential also. Okay, so do it. Don't wait for me. This is very simple. It's also from your book, textbook that you are supposed to open. You do the solve problem, you hide the solution, and you work on the solve problem. It's a good practice. You doing it? Okay. So what's the okay? So here we have to take potential energy equals to 0 here. And then here, the height is 1.2 meters. So I guess that height, yes, that height here is 4.8 meters. So it has potential before, potential after, and it has kinetic before. Okay, so potential before plus kinetic before equals potential after plus kinetic after. So do it. It's easy. We review for the final. It's very easy. Definitively on the final. Conservation of energy. It's very simple. So it's a good practice to do it with your TI. So potential before, it's going to be mg 1.2 plus initial kinetic energy, we don't know, 0.5 mv squared. Potential after, it's going to be mg 4.8, and then it's not moving. You see, it's very simple. But you have to do it, right? You say bye-bye, 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 and you are solving for the speed. So what do you get? 5.5? 8.5, yeah. So make sure that you multiply by 10. Maybe, because you didn't divide by 0.5. Don't forget to divide by 0.5. That must be why. 8.5. Did you all agree with that? Make sure you divide by 0.5 on both sides, and then you take the square root. Don't forget the square root. Now, you could have done a different way. You could have said the change in kinetic energy equals the change in potential energy. So you could have said that the change in kinetic energy equals mg delta h. Okay, it will be the same thing. No. Because potential energy is just mgh. It's kinetic energy that you have a square on the speed. Right? So you move it to the other side, or you move this one to the other side, and you so you get 0.5 v squared equals g 4.8 minus g 1.2. So you can factor out the g, or you can say 480 minus 120 if you want. And you divide both sides by 0.5 and you take the square root. Okay? So 54. Oh, by the way, like someone brought that to me, but you know, when you make a turn at the light to get to the campus, they are doing work and they use this technique here. Look at this. Have you seen that? So you have potential energy, and then they let go in free fall. That will turn into kinetic energy, and all that kinetic energy, it's going to be in force times distance. Remember, energy is force times distance. So because the distance it's moving is very small, the force will be huge. So potential energy, kinetic energy, force times distance. And they are doing it. I don't know the way they do it. Like they have a huge crane with heavy stuff and they let it go. Did you see that? Yeah, when you're about to turn, right? So that's at the marina all over. And they are putting a pole inside. And that's how they do it. And they have a rail, right? They have rails to guide the load. So it doesn't end up on someone's head. That will not be very nice. We don't want that. Okay? Easy just to practice, easy just to relax. So he starts from here and 5 meters. So he starts from 10 meters above the water. And now at 5 meters above the water, what's going to be the speed? So you see here, it's not done with the potential energy. It still have potential energy remaining. So it's here, it has potential and kinetic. Here it just has potential. Okay? So it's like Bitcoin, and then you cash in a little bit, but you still have some Bitcoin left, and then you have dollars, and dollars plus Bitcoin will be the same amount you begin with. So if there is momentum, you're gonna have force times distance, right? That's the idea of what I have show you. So don't forget all the physics, right? If there is a change in momentum, there will be a force times the time of impact. This is called the impulse. Remember that? So the impulse is the punch delivered by the force. I'm thinking of that because I know, did you watch Mike Tyson? Did you? It's fake, right? If I don't believe it. Now you see him training like the guy is a monster, is a beast, and then he's like waiting down. So anyway, when you are doing boxing, it's all about physics, right? You have a change in momentum. You do a cross, right? So you put all your body, so change in momentum. And when it's going to reach the face, it's going to be a force times the distance. And because you don't go too much into the face, so the force is, the distance is small, so the force is huge. Isn't that interesting? Conservation of energy, right? Kinetic energy and then force times distance. So anyway, or you can say change in momentum is a force times the time. If the time is small, the force is big. So let's go back to my business here. So before, so that will be 10 meters here. Okay. So you take potential energy equals 0. So does he have kinetic energy to begin with? No, very good. Okay, so it's all potential energy. So M, G, H is 10. Okay, no kinetic energy equals, and then here is 5 meters above. So here he has both kinetic and potential. So it's going to be mg5 plus 0.5 mv squared. Who knew physics can be fun? Look, this is super easy and super fun, isn't it? Right? So 0.5 v squared equals uh, equals what? 100 minus 50. Is that right? So v squared equals 50 times 2. Which is about 30, something like this. Do you agree? 33, right? It's easy. I did a mistake.
Yeah, right.
The square of what?
Yeah, I got some.
What 100?
The square root of 100.
No, but because it's
It's 550.
so it's 10 times so 10, so it's 100 minus 50. No, it's good. Square root of 100 is 10. Oh, you're right. Thank you. Yeah, you're right. It's 10. I don't know why. Thank you. Oh, I was checking if you were paying attention. Yes. Okay. So now what's going to be the speed when he reaches the water? So now there is no potential energy here. Yes, there is no potential energy here. There is only kinetic energy. So all your potential energy, which is mg10, mgh, will be 0.5 mv squared. So now it's going to be v squared equals 200. Okay, so v equals about 14. Thank you. Okay, so it's a easy chapter, right? Only the test one was hard, but then it gets easy. So to begin with, you have only potential energy, and then you're gonna have some potential and some kinetic, not half and half, so it depends. And then at the end, you're gonna have only the kinetic, but the total amount stays the same if there is no air resistance. So it's like a container, right? Okay, so let's try to do find the speed here. So we neglect friction. So here it's potential, kinetic, and potential. So it still have some potential here. Okay, so why don't you do it? So we are reviewing because it's nice. It's a roller coaster. So we suppose that there was no friction, no friction. If usually I don't have DRC, but if you have DRC for the final, you have to plan ahead. Okay, so super easy. So you decide that potential energy equals 0 here. So you have only potential, zoom, 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 potential and kinetic. So here you have the mass and g and 50, and then it's gonna go into mass and g and 5 plus 0.5 mv squared. So it goes bye bye, bye bye, bye bye. Okay, so what you get, the mass is 200 kilograms. So 500 minus 50 equals 0.5 v squared. So 450 equals 0.5 v squared. So v squared equals 450 and 450 is 900. So v equals, yes, 30. Is that good? A good physics problem should not be hard with the math. It should be as simple as that. So now for the MCAT, you know, you cannot have a calculator because you have that kind of computations. Okay, so roller coaster is like here, for example, you can, it's gonna swing back and forth. So here you have potential and then kinetic and then it's a pie I was looking for, right? So here it's blue, potential, kinetic. So it's swinging back and forth between the energy. But if you put some friction, so if I do something bad, let's do something. Yeah, pause it. It's like, I'm gonna take her and what's gonna happen here? So if I move it, so this is the same level, right? So if I put her higher, what's gonna happen? Right. It's gonna have too much potential energy. Yeah, no one is hurt. So this is fun. Like if you have a little sister or something like this, because you can build your own. You can build your own roller coaster. I don't know how you do it, but I know you can do it. I don't know. Um, Whatever. You get the idea. Projectile motion. Boom. There is no friction. She will keep moving ever, forever, foreafter. Okay, so now what's going to happen if the system is not isolated? So it means you start with some energy and you can put energy in. So for example, if you have a SpaceX rocket, okay, it has some kinetic energy, and let's say you turn on the booster, so you can add some energy in the system. So that's what happens when work is done. By another force, you add energy to the system. So you need to change this equation here. Now, if you have friction, you take away energy from the system. So let me give you a very simple example. Right? So let's say you have like a cart, like something here, and it's already moving. It has some kinetic energy to begin with. And here you come and you are pushing. So are you doing work on it? Yes, because it's moving, right? So that means you are doing work. That means you are transferring energy from you. Work is energy transfer to the system. So let's say the force here is the force here that you are push is the applied force. Okay, so there will be an acceleration. Remember, there is a force, there is an acceleration, and now it's going to move faster. So is there an increase in kinetic energy? Does it move faster?
Yeah.
Yes. So how I can write the equation now? What is the energy you begin with? So kinetic, very good. So 0.5 mv watt square plus what? Plus the work. Because remember, work is like you have energy, like from burning ATP, phosphate bond, or whatever it's called. Okay, you are burning energy, and that energy you pour in the system. So that will be work done, so applied force times the displacement. Remember, that will be the work done by you on the cart here. Because you add energy. That will be equals to 0.5 mv final square. Does it make sense? Right? So what's happening here? You had energy to begin with. So that was kinetic energy. and you come along and you say it doesn't go fast enough. Okay, maybe I'm gonna turn on the booster. Okay, so it has some kinetic energy to begin with, and then you're gonna add more energy because you are doing work on it. So at the end, it's gonna be all kinetic energy. Okay, all that turns into kinetic energy. That's how it works. So when you are doing work on something, that means you add, and if the work is negative, you remove the energy. Is that clear? So the different way to say it, like we have learned that before, is to say the net work done on the card will be equals to the change in kinetic energy. Remember that? It's called the kinetic work theorem. So what is the work? Is the force. So you apply force times the distance equals a change in kinetic energy. Isn't that wonderful? We are reviewing for the final already. We are ahead of ourselves. Wonderful. It's the same thing. This and this is the same thing. So the work kinetic theorem is the same thing as conservation of energy. Is that clear? Right? So let's change it a little bit. Let's say now that you have friction. A little bit of friction, not much. It's still going to go faster, but you have a little bit of friction. What's happening with the friction? Is it doing positive work, negative work, or no work? Negative work. So what's happening? It's stealing away energy. It's an energy fifth. So it means work is negative. It's taking energy away. Agree? It's trying to make it go slower. Okay, friction is always doing negative work. So now I can write, okay, the energy that I had before plus the energy I'm investing in. So put in, so I'm adding energy, minus the work done by friction. So it's stealing energy equals whatever is left. Okay? So it's like you have money in your bank account. You put some money more money because you have a job, so more money comes in your bank account, but then you have to pay for your rent, so you are losing. So whatever was in your bank account plus what you put in, or your boss, your job, put in, and then minus whatever withdraw. So that's how it works. Now you can also say the net work equals the change in kinetic energy, and that will be the same. The net work will be the net force, which is the force applied, minus the friction times the displacement equals the change in kinetic energy. It's the same thing. It's the same thing. So you have to think of energy like money. You put in the money, you remove the money. It's accounting. Okay? So that's what I was trying to explain. So in that case, you see, you start, let's say potential energy equals 0 here, and it's not moving. But you're going to put energy in the system because there is an explosion. So actually, what type of energy is that when you have a TNT or an explosion or a booster? Huh? Combustion is what kind of energy? Potential energy, right? It's chemical potential energy. So for example, we have fat. The fat is chemical potential energy. We're gonna burn the fat with oxygen. Okay, we're gonna release energy, water, and CO2. Okay, but it's chemical potential energy. When you have fuel, you are right, it's combustion. What type of energy is fuel? Chemical potential energy. Why? Because to release that energy, you have to break the bonds. By breaking the bonds, there is a transfer of electrons and energy is released. And they call that in biology, I never understood how it works, ATP. All what I learned by heart is that it's called energy currency. I don't know much, but that's the idea. Okay, so knowing that, can you help each other, talk to each other, and try to solve that? And don't stare. I see big eyes like this. Don't give me the big eyes. Do it. Do it, do it, do it. Even if it's wrong, you take a pen and an eraser, or you take your tablet and you try. And you can talk to each other. So we're going to say here, potential energy here is 0. Okay, so here it has some potential energy. But some energy is chemical. You have chemical potential energy and you burn that. You burn that. So you can say potential energy, gravitational potential energy, there is no. Kinetic energy, there is no. Plus, you put energy in, which is chemical potential energy, combustion, E equals the final gravitational potential energy plus the final kinetic energy. Okay, so it's like you have your bank account and someone very nice put money, you get money for your birthday inside your bank account. So that will be 0. That will be 0. There is no energy to begin with. Do it, do it, do it. Don't be on your phone. You're being efficient with your time if you are not spacing out. So how much energy is being invested? So you have 425 equals potential energy after you have mg, and you are missing one information. Apologize. You are missing the mass. The mass is 200 grams. Okay, the mass of that, I don't know what it is, a rocket. Mg h plus 0.5 m v square. Do it, 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 do it. You know, if you work here, the homework will go quicker, and your review for the final. And ChatGPT is a very bad idea because you don't learn anything. So the mass mgh 1/2 mv square. I don't know if it's well written. The mass is 0.2 kilograms because it's 200 grams. Okay, you doing it? So 425 equals, so here we have 0.2, g is 10, the height, the final height, plus 0.5, the mass, 0.2, and v square. So you isolate your v square, you're all very good at algebra, you have to, and then you take the square root. So what do you get? Yeah. Is that Gabby? Yes. 61, no? 61. Do you all get that? I don't need to do it with the TI? So with the TI, you do 425, enter, minus 0.2 times 10 times 29, enter. And then you divide by, open the parenthesis, 0.5 times 0.2, close the parenthesis, enter, and then you take the square root. Okay? So what's happening here? That's your energy container. And to begin with, you have no kinetic, no potential. Everything is in chemical, in fuel. So it's chemical potential energy. And then there is oxidation, something like this. Okay? And everything goes into potential, some potential, and then here some kinetic, but the level here will be the same if there is no friction. So you go from chemical potential energy to kinetic and potential. Okay? So by the way, for the human being, it doesn't work that way. It doesn't work calories in, calories out. It doesn't work. Except if you have no insulin resistance. But otherwise, we are not a machine. So calories in, calories out, nonsense. And unless you are young and like you. If you are young like you, that's fine. Okay, so here is an example. I don't know if I show you this example. I think I did. So in skateboarding, you want to go half pipe. Okay, so begin with kinetic energy. Agree? And here you're going to stop there. You have all potential energy. But if you want to increase the height, you're going to squat and extend. By doing that, you are doing work, force over a distance. So you are increasing the amount of energy. So in that case, you're going to say kinetic energy plus the energy done by your muscles equals mgh. Same thing. It's called to pump. But it has to come from somewhere. Nothing comes for free. You have to squat. And when you squat, it's a force over a distance. Okay, now if you have friction, instead of adding energy to your system, you are removing energy from the system, right? So that will be minus the force of friction times the displacement. The force of friction is always along the path. Okay, so for example, we are like 20% efficient. All the energy that we burn goes into heat and not necessarily into moving. So we are not a very efficient machine. Okay, so friction, remember, it's a kinetic friction will be the coefficient times the normal force times the displacement. So kinetic friction is always along the path, right? Remember that? Okay, so let's do number 1, just for fun. Easier. It's an easy unit. It's an easy unit. And some of you told me you want to take the MCAT. I highly recommend that you start practicing the problem in your book. Conservation of energy, for example. It's very easy. Okay, it's easy. So help each other. More you do now, less you have to do at home. So kinetic energy, 0.5, the mass times the speed square. So number 1, so 0.5, the mass, so 1000, the speed square, so 30 square. Okay? number 2, kinetic energy is 0.5. Now, the mass is half, but boy, yes, the speed is double. So, so this one will have twice the amount, yes? Because if, remember that, typical question, assignment or final, if you multiply the speed by 2, the kinetic energy is multiplied by 4. So kinetic energy is divided by 2 because the mass is divided by 2. But at the same time, it's going to be multiplied by 4. So it will be multiplied by 2. So this one will be multiplied by 2. If you do not understand, all you have to do is kinetic energy of number 2 divided by kinetic energy of number 1. So you know how many number 1 goes into number 2. And you do the math. Yeah, 500 times 60 square. No, it's the opposite, right? Yeah. So it will be 0.5 times 500 times 60 square and 0.5 times 1000. Make sure you put everything in the parentheses here, and that should be equals to 2. Agree? So typical conceptual question they like to test. Okay, the mass is divided by 2, fine, but the speed is multiplied by 2, which is the energy is multiplied by 4. So 4 and then divide by 2 is 2. So kinetic energy is a killer because you just increase the speed by a tiny bit and then the damage, the potential for destroying increases by a lot. Okay, number 2. Okay, number 2. Just for fun. So don't stare. Do it, do it, do it. Is that big enough or it's not big enough? It's good? Do it, 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 do it. 63. It's possible sometimes I update my slide. Uh,
Yeah.
so I have updated my slide so you can download the new version. So this is 2 kilograms. So remember, don't confuse mass and weight. So this one has more weight, but more mass. Less weight, but less mass. So you can solve that by kinematics if you want. So mgh equals 0.5 mv squared. And surprisingly, the mass does not matter. Remember, on the moon, you have a hammer and a feather, and they are dropped from the same height. They will reach the ground at the same time, with the same speed, and they will have the same acceleration. So you always have square root of 2gh. Divide by 0.5 is like multiplied by 2. So the speed is what? 2 times 10 times 10. So you're gonna get 14.
Yeah.
Okay. Okay, add down. But. So here it's fine. They have the same speed. However, they're gonna hit the ground. So they're gonna hit the ground. They're gonna push the ground. The ground is gonna push back to stop the mass, right?
Mhm.
So let's see if we have the same change in momentum for both. And remember, it's not the falling that kills. Yes, it's the landing. So even though they have the same speed before they're gonna hit the ground, let's find the change in momentum for 2 kilograms. And it stopped, right? It's gonna stop moving here. Okay, so do it. Yes. So the mass, remember, change in momentum is the mass times the final velocity minus the initial velocity. Okay, so the mass is 2, final velocity is 0, minus initial is 14, so it's gonna be minus 28 kilogram meter per second. So that will be the change in momentum, yes?
Mhm.
However, for the one with a 4 kilograms, look at that. It's going to be 4 times the final speed, 0 minus 14. And now I'm going to have minus 56. So you have a ratio of 2. So that means, remember the physics here, the change in momentum equals the impulse. What's an impulse? It's a punch. It's a punch delivered by the force. Yes. So here they're asking me for the change in momentum, not the change in kinetic energy. So don't confuse, right? The change in momentum is the mass times the final velocity minus the initial velocity. So test number 3, don't forget, right? The change in momentum is the mass times the final velocity minus the initial velocity. By the way, momentum is a vector, so it could be positive or negative. When you have conservation of momentum, the total momentum before equals total momentum after. So this is a vector. So the change in kinetic energy will be 0.5, the mass, and here we have a scalar. It's a scalar, I square. It's a speed square minus a speed square. This is a vector. So for example, if something bounces off, you add the velocity. Did I answer the question? Yeah. So don't confuse both. It's a good question because momentum can be plus or it could be minus because it's a vector. But energy, kinetic energy is a scalar. So if the change in kinetic energy is negative, it just means you lost speed. Okay, it doesn't mean that the direction is to the right or to the left. Momentum is negative, it means it's to the left. So you remember when something is bouncing off, remember when something is bouncing off, this is the initial and that will be the minus. So the change in momentum will be the mass minus 10 minus 10. Okay? But a change in kinetic energy is a scalar. Is that clear? Now remember, that change in momentum, okay, from Newton's second law, if there is a change in momentum, that means there is a force times time, so that will be the force of impact times the time of impact, and this is called the impulse. So what is a impulse? Is a punch, a kick delivered by the force. So what does it mean? It means here it's gonna hurt twice as much. It means that the impulse to stop it will be twice as much. So someone falling, skinny or heavy, it doesn't matter when you are in free fall. What matters is when you're gonna hit the ground. That's gonna hurt. Heavier you are, worse it will get, because the force will be larger, because you have more inertia. So it means you need a larger force to stop you from moving. So what kills is the landing, it's not the falling. Is that clear? Mm-hmm. So change in momentum, larger is the change in momentum, more force, more punch. So for example, if you do boxing, for example, you have a large momentum, change in momentum, and all that goes into force times time. But the weight of your gloves matter. If you have heavy gloves, of course it's gonna hurt more. So I was teaching this class, and someone told me there is a show about crime investigation or something like this. So there is this boxer who wanted to kill his partner, right? So have you seen that show? So what he does, because you are all in chemistry, you know how mercury is a very heavy metal. So he injected mercury in the gloves, right, to make it very heavy. So it will have more change in momentum because it has more mass, so it will be more force, right? And he killed his partner, right? Because you increase the mass, you increase the momentum. Isn't that interesting about mercury? And then they find out, because this, so I don't know how you can see mercury, leaking out or something like that. I don't know if it's realistic, but I thought the idea is good. Plus, you need to get mercury. I don't know how easy it is to get mercury. You can get mercury. I know you can buy it online. You can buy it online. You can? Yeah. Oh, you can? Oh. Do you know the density of mercury?
Uh, no, but I know it's like up there,
Up there, right? It's
way denser than gold, but it's not as dense as osmium.
how much?
14 grams per cubic centimeter.
So 14. So 14 times heavier than water. What about gold? Is it heavier?
I think the heaviest is osmium. That's the densest.
Gold is 19.
19. So it will be better to put gold into your gloves, right?
Yeah, but that costs so
Right.
much money.
Oh, yeah, you're right. No, mercury, because mercury, it's a liquid, right? So I guess it's easier to hide. Okay, so that's a tangent. But I thought it was interesting.
Yeah.
Okay, let's do this one. So that one comes from the book uh, Conceptual Physics. I think everyone should learn boxing because it's a very good therapy. Like if you are very mad at your physics professor and she has this weird accent, you cannot stand it anymore. You do some boxing and then you love your professor. Okay, so work done by a force on a system equals the force and parallel. It has to be parallel to the displacement times the displacement. So what about Jim? So he's pushing a desk and the desk does not move. even though the force is huge. Is he doing work on the desk? No, because you are doing work if you can increase or decrease the speed. If it doesn't go anywhere, no work, zero. So of course he's puffing and huffing, but he's doing work on the molecules around him. Maybe he's getting sweaty, but it's not doing work on the desk. Okay, let's do for Virgil. So it's going to be the force, 400 times what? Times 2. You see, they try to trick you. It's called TMI, which is 800 joules. And then Mick, I don't know what kind of name is that, so it's going to be 200.
Mike.
Mike. It's Mike. Right? So it will be what? 100. So you can either increase the distance or increase the force. So it's when you have a machine, for example, it's a trade-off between the distance and the force. And I think the pop quiz is open.
Yeah.